yesterday we talked about compound interest and compounding more than once a year. The annual compound interest formula is something we dealt with before, but yesterday we introduced this formula. And this formula takes into account compounding more than once a year. And we found out that if you compound twice a year, you make more money than you do one time a year, even if you don't change the investment or the interest rate. And then we looked at like quarterly and monthly and daily and so on. So today we're going to look at how much compounding it more and more actually affects the dollar value. Okay? So, top of this worksheet, suppose you have a bank account that collects compound interest. The bank has a plan where you can pick how many times per year the interest is paid. So you can tell them how often you want them to put the money in the bank. Sounds like a good idea, right? The catch is that the bank charges an increasing fee according to the number of times the interest is paid each year. You plan to invest $2,000 at 8% for 5 years. Using the fee chart below, determine the number of compounds per year you will earn. Excuse me. All right, so let's look at this chart on the top. So compounding annually, how many, that would be compounding at one time, so n would be 1. Semi-annually would be 2. Quarterly would be 4. Every 2 months would be 6. Monthly would be 12. Weekly, 52. Daily, 365. And then how do we figure out hourly? 365 times 24 hours per day, 8,760. How about every minute? So times this by 60, 525,600 times every second, times it by 60 again. So just for your information, there are 3.1 million seconds in a year. So, well, no, you got to write it out because we're going to put these in our calculators. And 3 times a second. So, 9,460,608,000 times. So, next to those numbers are the one-time fees that are going to be charged at the end of the 5-year period. So if you pick monthly, they're going to compound your interest 12 times per year for 5 years, but before you take your money out, they're going to charge you $8. So, if you had to guess, which account do you think is the best deal? Which one is going to yield the most amount for 5 years? So one of them is going to be more than all of the others. And the question is, obviously, if you compound 3 times per second, so they pay you interest 3 times per second, they're going to pay you 9.4 million times. Is that going to be worth the $14 they charge you at the end? Actually, it doesn't matter how long they leave it in. Well, okay, maybe it does. But they're all for 5 years. Yeah, I guess it would. Okay, so go ahead and guess. You need to pick one. I don't care. Can't get this wrong. Yeah, this is the question right here. Okay. So, for the next chart, use the compound interest formula to calculate how much money will be in the account after 5 years. And then the fees will be assessed at the end of that 5-year period. So I'm going to highlight these and move them over. So we look down here, and it's actually going to be easier if we start at the bottom and work up. Because if we start at the top, we're going to have to do second insert a whole bunch of times. If we start at the bottom and work up, then we can just do type right over and use the delete button. So, what do I plug in this equation for 3 times per second? So we take our $2,000, we times it by 1 plus, the interest rate is 8%, turned into a decimal is 0.08, divided by n, which in this case is 94608,000, raised, and oops. I don't have to have parentheses in my exponent, but if you have the little caret button that shows up, then you do need parentheses. But my version doesn't need it. So I type that number in again, 94608,000, and I'm going to times that by t, which is 5 years. Good. So, $2,983.65. And make a note, I want you to write out that whole decimal. We're just going to save that for later. Okay? And at the end of 5 years, I'm going to be charged $14, so I need to subtract $14 off of that. So 2969.657. Okay. Now we're just going to go up through the chart and fill in all the other values. So I'm lazy. If I push second enter, that brings up the previous equation. If I push second enter again, it brings up the one above that. And now I just need to change these numbers. So I'm going to type in 3153600, and then plug that number in the exponent also. 3153600. What do you notice? How much of a difference is there? So we have tens, hundreds, thousands, 10,000s, 100,000s, millions. It's 1/1,000,000th of a penny less than the one before. Well, I mean, that's really not very significant. Even if there were 1,000,000 transactions, that's still 1 cent. So it's really not that much. So which is a better deal, every second or 3 times a second? Every second, how come? Well, so these two numbers are the same. I mean, they're not going to pay you 1/1,000,000th of a penny. But why is every second a better deal? They charge you less in fees. So you're actually going to make a dollar more if you use the every second as opposed to the 3 times a second. So go back up, fill out the rest of that chart and all the ending balances, and then answer the questions on the left side. So if you're at home, pause the video, fill out that chart, and I'll be back in a second. Okay. Welcome back. So, which option will make you the most amount of money? Weekly. So if you look here, you make 22 cents more weekly than you would daily. That's kind of strange. So the next question asks, what did you notice about the interest as n gets larger? So, I mean, that's true. You're taking out more, and I didn't let her finish. So, what happened with the interest? And maybe you didn't expect it. The difference between one n value and the next n value got smaller and smaller and smaller. Would we suspect it to eventually stop? Like an asymptote? Yeah. So you may have assumed, well, turn the page. So the top of this page says, it is now quite obvious that there is a limit on how much an account can grow as the number of compounds per year increases. We will now explore what that limit is. Essentially, we are asking what happens to the compound interest formula as n approaches infinity. So we're going to use our calculators to figure this out. So just take the notes that I'm going to write in this space. So Connor brought up the idea of an asymptote, so you don't need to draw this one. But we've seen graphs that kind of look like this, where graphs approach particular lines but never actually reach them. And asymptotes are straight lines. In this case, we have sort of a curved asymptote. So draw this graph. Well, let's do it this way. So if we were to look at the graph of our $2,000, so we start here at 2,000, if we compound annually, the graph might look like that. What is the graph going to look like if we compound semi-annually? A little bit steeper. So semi-annually, it might look something like this. So the first one is n equals 1, and the second one is n equals 2. And every time you increase your n, the graph is going to be taller. But if I increase to n equals 3, how will that compare to 2 as 2 compared to 1? Right, so the difference between 1 and 2 is going to be a little bit bigger than the difference between 2 and 3. Because as n gets larger, you're still increasing, but you're increasing at a decreasing rate. So we can have a whole bunch of graphs. This one might be n equals 12, and n equals 365. But the higher and higher we get, the closer and closer those lines are to each other. So you may have assumed that compounding 9 million times a year would create a graph that was super steep. But it's impossible. The steepness of all of these graphs is determined by one limiting factor. What is it about the equation that tells us how steep any particular curve can be? The interest rate. So this interest rate is 8%. There is a limit on how fast an 8% equation can grow. So there is some curve that is higher than all other curves dealing with 8%. Does that make sense? And really, all 8% curves look sort of the same. So, somewhere is this theoretical line that represents the highest increase an 8% graph can achieve. Well, what is the n value for that graph? Infinity. So that blue dotted line is the graph when n equals infinity. The trouble is, well, let's actually write out the equation. So if I take 2,000 times 1 plus 0.08 over infinity raised to the infinity times 5, I have a couple problems. First of all, what is 0.08 divided by infinity? Not infinity. That 0.08 times infinity is infinity. If I take 1 and divide by 10, I get 0.1. If I divide by 100, 0.01. Divide by 1,000, 0.001. 0.0001. So what happens as the denominator gets bigger? The number gets smaller. So this number has an infinite number of zeros and then an 8, which is actually 0. If I take 0.08 and I cut it into an infinite number of pieces, how wide is each piece? It's really small. So this number is almost 0. Well, that number is infinity. So 1 plus almost 0 is really close to 1. And 1 to the infinity is 1, but 1 point almost 0 to the infinity just creates problems. So we try to do that, and the equation falls apart. So, using calculus and some other things that you guys don't understand, we can actually change the equation. We can convert this to another form. And to be honest with you, I don't even know how to do it. I looked and looked this morning to figure it out, and I found a proof that was like 4 pages long, and I gave up. So, we can change this equation to look like this. P times 1 plus 1 over n raised to the n, and then all of this gets raised to the RT. So in our particular case, it would be 2,000 times some number raised to the rate times time. Okay? And we want to know, what does that number equal when n is infinity? Okay? Well, here's how we're going to do it. And you don't need to type this in. You can just watch. So I'm going to type this into my graph. 1 plus 1 over x raised to the x. Zoom standard. And you can see, well, let me change my window. 0. Oh, oops, wrong button. Oh, yeah. Yeah, and it didn't even look like it was the right proof, so I don't know how to do it. So you can see, this is the graph of the number that fits inside this equation. Okay? And as n gets bigger, the equation kind of levels off. So it starts somewhere above 1, and then it goes up through 2 and a little bit bigger than 2. So if I push second calc and go to value, I plug in 1, and the value is 2. So if n equals 1, then the value inside that equation is 2. 3 will put me at 2.3. 9 will put me at 2.58. But we need a really, really big number. So I'm going to change my window to like 10,000. And you can see when you look that far out, it's pretty much a straight line. So second calc value. So I'll plug in 100. I could. Well, okay. You want to see trace? Oh, that's graph. I can't read mine. Okay, so as I go to the right, 2.71. Oh, really? So if I want 3,000. Oh, that's nice. So 2.717, 4,000, 2.7179, 5,000, 2.718, 10,000. Oh, that's too big. Oops. So 10,000 is 2.718. We've pretty much maxed out. So the number that goes inside here is 2.718 and some other numbers. Well, that number is really significant, and it has other ramifications in calculus that are hugely important. So we call this number E. So E is the limit of this piece as n approaches infinity. Now, can we ever actually get to infinity? No, but using calculus and limits, we can figure out what it would be if we could get there. Does that make sense? Well, there's a good way to explain it. Let's say that we had a graph that had an open circle at the end. And let's say that this graph is like 1 over x plus 2. Well, x minus 2 would be a better idea. 1 over x minus 2. Okay? So there's this gap, because if I plug in 2, I get 1 divided by 0 is 1 divided by 0 is infinity. It's undefined. So there's a gap at x equals 2, right? So the number doesn't exist. But if I trace down this way and I trace up that way, can I narrow down what the number would be if it was gone? Yes. And that's called a limit. So the limit of this graph as x approaches 2 would be whatever that number is. I don't know what it is, 2, like 2 comma 2. Even though it doesn't exist. And we do the same thing with infinity. Right, which would be 2. Yeah. So that's what we do with limits, is limits help us find the answers to things that we can't figure out because we get errors if they would really exist. So, going back here, so the graph of the blue dotted curve is actually P times E to the RT. So, you look at your calculator, above the divide key is an E. So second E, 2.718, which is what we figured out by the graph. Now, this is a number very similar to pi. It's irrational, it goes on forever, it shows up all over in mathematics, especially in calculus. Yes. Yeah, it's the exponential number, that's why we call it E. And this equation, PE to the RT, represents compounding an infinite number of times. Now, can that really happen? How many instances are there in a 1 second interval? An infinite number of instances, right? So continuous interest, that's what we call this. Continuous interest means every instant you earn an instant's worth of interest. So the bank is always paying you an infinite number of times every second, which theoretically can't happen, but mathematically that's the equation. Okay, so the dotted line in this case is 2,000 times E raised to the point, what was it, 0.8, 0.08 times 5. And that's exactly the same thing as using the other equation and plugging in infinity for n. Okay, but how different do you think this is going to be from that every 3 second thing that we did on the back page, on the front page? Hardly different at all. What was the difference between every second and 3 times a second? 1/1,000,000th of a penny. So what's the difference between 1 second and continuous? Almost nothing. In fact, the difference from daily to continuous is not very much. Once .n gets around 300 or 400, it doesn't get much bigger after that. So you can only make the graph so big, and every time you increase the n value, the rate of change diminishes. That makes sense? So, you want to see something that's really going to blow your mind? Let's calculate this. There's another E button right here above the ln, and it comes with an exponent button, so that's kind of nice. So 2,000 E raised to the, and it's 0.08 times 5. So let me kill this and steal somebody's paper. It's still yours. And hit enter. What do you notice? Anybody confused? It's smaller. Why is the number on my calculator smaller than that number? The reason is E in your calculator only has 9 decimal places. Well, 8 decimal places. Okay? And that's less accurate than using the other formula and plugging in 9 million. because as an exponent, 9 million in the exponent is worth a lot more decimal places than 9 decimal places in a base. Does that make sense? So that number that we calculated on the other page is actually more accurate because the E value in our calculator only has 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 decimal places. So we would need 20 or 30 or 40 or 50 decimal places in order to get a more accurate number. But, I mean, really, we're talking about like half a cent, right? What was the difference? It's not very much. A little more than half a cent. So, really, this number is not accurate because the E value gets cut off. If we had a lot more decimal places, then it would look a lot like the one before. So that's just a little quirk with the calculator. So using the other formula with really big numbers is more accurate than using the actual formula with E. But, I mean, we're not talking about very much money, so we'll just forget it. Okay, so number 1 on the back. If $18 is compounded continuously at 7%, how much money will there be after 9 years? So 18 e raised to the .07 times 9. $33.79. That's if they paid every instant. Now, my bank calculates interest every day, but they don't pay the interest until 3 months have gone by. So mine's compounded quarterly. Yeah. Yep. Okay, number 4. If hang on just a second. If $250 is compounded continuously at 4%, how much money, more money? Ooh, good. Will there be after 6 years than if the same amount of money were compounded annually for the same 6 years? So we're calculating 2 different versions. We're going to calculate continuous, and we're going to calculate annual. Which one's going to be bigger? Continuous will be bigger. The question is, well, no. In order for the calculator to not be accurate, you need to do like every second. So we should be fine. So this one's going to be bigger. The question is asking how much bigger. That's what we're trying to find. So we need to use the new formula, 250 e raised to the .04 for how long? Times 6. So we get $317.81. And how do we calculate annual? So 250 times 1 plus, oops, I forgot parentheses. 1 plus 0.07 divided by 1 raised to the 1 times 6. Oh, what did I mess up? Oh, 0.04. Sorry. The interest rate is not 7%, it's 4%. Connor. So this one is 316.33, which is a difference of $1.48. And that's not very much because, for one, the investment was pretty small. 2, the interest rate is pretty low. And 3, 6 years is not a long time. So that's not a very big difference. But if you raise any of those values, the difference will be greater. Yeah, you'd still rather have continuous. But in the real world, continuous and daily are very, very similar. So when you get a loan, they charge you daily interest, which is really, really close to continuous interest. There's not that much difference. All right, that worksheet is due tomorrow.